Hello, this is our second video on logic, and this video is really all about implications. Okay, so one of the major goals of this course is proofwriting, and this is true for both the computer science and the mathematics majors. We really want you to be able to learn, to really understand and feel comfortable with proving statements, whether they're in algorithms and theory of computation, or whether they're in abstract algebra and real analysis. Okay, so the kinds of statements you'll be proving in any of those courses are implications. So we really have to come to grips with the logic of implications. So the learning goals for this video are that at the end, you should be able to explain using a truth table when an implication of the form P implies Q is true. You should be able to formulate the converse of an implication, and you should also be able to formulate the contrapositive of an implication and explain why the contrapositive is logically equivalent to the original statement. Okay, so let's begin with the definition of an implication. So if P and Q are statements, then P implies Q is the same thing as saying if P is true, then Q is true. And we often write that as P, and then with this funny arrow that has two bars, implies Q. And those two bars are really important. In mathematics, when you see an arrow, when you see an arrow that's written like this, it really exactly means the word implies. Okay, so let me just find my examples over here. Oh, before we do an example, let's look at the truth table for this. So when we make our truth tables, remember, we look at all the possible combinations of truth values for P and Q. So both true and one false, and both false. And then we look at the compound statement, which in this case is the implication P implies Q. And let's see in what situations the compound statement P implies Q is true. Okay, so it's true if P, the premise is true, and the conclusion is true, then the statement is true. If the premise is true and the conclusion is false, then P being true did not imply that Q is true, and so the statement is false. What's a little bit sometimes trickier to wrap your head around is that if the P part is true, if the P part is false, then the statement is automatically true. Okay, and we'll talk about that in a few minutes. Let's start with an example though. So for example, suppose our P statement is the statement, the empty set is an element of A, and our Q statement is that the set containing the empty set is a subset. So is a subset of A. So I can write the statement, when I write the statement P implies Q, there are some different ways of rewriting that. So I could rewrite it in symbols. So these symbols stand for the empty set is an element of A, and then I could write that symbol for implies that the set containing the empty set is a subset of A. I could also write it partially in words. So I could write it as an if-then statement. So if the empty set is in A, then the set containing the empty set is a subset of A. And I could even write it completely in words with no logical symbols at all. So I could write if the empty set is an element of A, then the set containing the empty set is a subset of A. Okay, and so here are now several ways of writing the same thing, and I just want to pause briefly and sort of think about like which one is best. Okay, so let me just change pen colors. So this one, that one means, you know, they all mean the same thing. This one purely in symbols, you know, we can extract the meaning from it, but it doesn't look like a sentence, right? It's not a sentence that we would recognize. This next one looks like a sentence. It starts with a capital letter. It has a couple words in it. It ends with a period. And I think it's pretty easy to understand the meaning as long as you remember what all the symbols mean. What about this last one? If the empty set is an element of A, comma, then the set containing the empty set is a subset of A. To me, at least, that one is not so easy to understand. It's like very wordy and I kind of like don't know what to pay attention to a little bit, like, oh, so many words. So, I mean, it's a little bit a matter of taste, and you'll find the balance as you write more. But I would say this one is a little bit too wordy. It's a little bit hard to take in at a glance. I kind of like this middle one the best. There are words, it looks like a sentence, but also like once I've really got the meanings of those symbols, the meaning just pops out at me and I can read it quick and understand it quickly. And really the point of this course, one of the points, is to learn how to be a good mathematical writer. And what good mathematical writing is it's clear. And it's easy for the reader to understand. So when you're trying to make these decisions, how much goes in symbols, how much goes in words, I think what you'll find usually is too many symbols and it becomes unintelligible because it doesn't look like thoughts and sentences anymore. And too many words, it's just hard to figure out what the mathematics is. So there's a balance and you'll have to find that. Okay, so that's one example. And let's see, let's try to find another example. So for example, I could say, suppose if the size of the empty set, the cardinality of the empty set is equal to 1, then the set containing the empty set is a subset of A. Okay, oh, you know, first I should just, we should just think about, is this first example, is the statement true or false? If the empty set is an element of A, then the set containing the empty set is a subset of A. So you can pause and think about it for yourself. It's true, right? Because if the empty set is an element of A, well, when I think of all the possible subsets of A, one of the subsets is I can take the set containing just that element. So that original statement is true. So I'm going to say this is true. Now let's think about this one. If the cardinality of the empty set is 1, then the set containing the empty set is a subset of A. Well, let's think. This is the P part now, right? And this is the Q part. Is the P part true? No. What's the cardinality of the empty set? Well, the empty set is the set containing 0 elements. So the cardinality of the empty set is 0. So this part is false. And the second part, well, it doesn't actually matter what happens with the second part, because I'm saying what an if-then statement is saying is like, if the first part holds, then I have to say something about the second part. But if the first part doesn't hold, all bets are off and the statement is automatically true because sort of I'm not making any promises that I can't keep. So this is automatically a true statement because we're in one of these two situations, okay, where an implication is true, has to be true if its premise, the if part of the if-then statement, is false. Okay. So what else can we do with implications? So a couple other things that we can do with implications. We can form their converse and their contrapositive. So definition, the converse of an implication of the form P implies Q is Q implies P. So you literally just turn it around, right? So for example, the converse of the statement, the empty set is an element of A, implies the set containing the empty set is a subset of A, is the set containing the empty set is a subset of A, implies that the empty set is an element of A. So in this case, let's think about whether this is true or not. If the set containing the empty set is an element of is a subset of A, it must mean that everything in that set is an element of A. In particular, the empty set is an element of A. So this statement is true, okay? The statement is true. And so in this case, both P implies Q, the original statement, and Q implies P are true. So both P implies Q and Q implies P are true. But this isn't always the case, and it's not the case in our example, other examples. So, but if we look at our other example, maybe that's really a but with a comma. But if we look at, so the converse of, so the second statement was that if the cardinality of the empty set equals 1, then the set containing the empty set is a subset of A. Okay, so is that, let's look at the converse of that one. Oh, I guess that's, yeah, that's a true state. So, okay, but the converse of that is if the set containing the empty set is a subset of A, then the cardinality of the empty set is equal to 1. Okay, so here's my P and here's my Q. And I want to know it. Is this implication true? Meaning always true. Well, is the Q part ever true? No, the Q part, that is always false, right? Because we know that the cardinality of the empty set, which is the number of elements in the empty set, is equal to 0, not 1. And it's possible for this other part to be true. So for example, suppose that A is equal to the set, the empty set, comma 1. So then, when that's true, the empty set is a subset of A, but of course this is not equal, so that's false, i.e. The converse is false. So this statement is false because it's not always true. Okay, I can find an example where it's false. And the example I found is an example where this part is true and this part is false. So we're in that second row. If you look back in the truth table, we're in that second kind of row of the truth table where you have the premise part is the premise part is true and the conclusion part is false. Okay, and then finally, I guess maybe it could be confusing here where my P's and Q's are. If I kept the same P's and Q's from before, I guess maybe I should call this one the Q and this one the P, because that's what they were up here. This is the P and that's the Q. Okay. Okay, let's talk about the last thing is the contrapositive. So definition, the contrapositive of P implies Q is the statement not Q implies not P. Okay, so let's think about the contrapositive of one of our first example. All right, so if we start with the original, which is that if the empty set is an element of A, then the set containing the empty set is a subset of A. So this is my P and that's my Q. Then the contrapositive is not Q. So if the set containing the empty set is not a subset of A, then now I have to do not P, the empty set is not an element of A. And if we think about this, this is true, and it actually means exactly the same thing as the original statement. It's logically equivalent. Let's use a truth table to understand what that really means. Okay, so I'm going to have, as usual, columns for P and Q and rows that give me all of the different combinations of truth values for P and Q. Now I'm going to make some extra columns. I'm going to also make columns for not P and not Q. Right, so the negation of P is false when P is true and true when P is false. Similarly, the negation of Q is false when Q is true and true when Q is false. Okay, and now I'm going to look at, given this information, when is not Q implies not P true. Okay, so I'm going to pay attention now to just these two columns, and I'm going to remember that an implication is true if the first part is true and the second part is true. So that's down here in that last row, okay? It's false. There's only actually one bad time when it's false. It's false when the first part is true. It's false when the first part is true, and that's here, and the second part is false. So it's false here, and it has to be automatically true whenever the not Q part is false. So it's going to be like that, okay? Now, let's also think about the original statement. P implies Q. That's true. Now I'm going to look back at my first two columns. That's true exactly when P is true and Q is true. And the only time it's false is when P is true and Q is false. And it's true the other times. And so what I can see here is that when I look at the values, the truth values for P and Q, and then I look at the truth values for not Q implies not P, and P implies Q, these two columns, I'm going to try to highlight them. These two columns are exactly the same. And so what that means is, if the statement P implies Q is true is exactly the same as saying the statement not Q implies not P is true. And sometimes what we'll see is that the contrapositive is easier to prove than the original statement. Okay, let's see, should we do one example before we go? All right, so one example. So suppose like our example with our original statement. Oh, we did the example already. Huh. We did it above here. All right, so you'll have lots of time to play around with examples in the pre-class questions. And then in class, we're gonna start digging in to some more complicated ones to really make sure our brains have thought around all the different kinds of combinations and trying to find subtleties and see the things that can happen. Okay, thanks.